Good morning. All right, good morning, everybody. So today we are doing review. I've got all the slides pulled up from each of the chapters. I will start going through that. We'll just kind of real quickly blow through things, and I will be like, oh, hey, this is important for you to know. If you've got questions, you just tell me to slow down and say, hey, could you go into that a little bit more? If there are things in particular that you know for sure that you want to cover or go over, we could start with that if you would like. So I'll throw that out there. Is there anything in particular that you think you want us to cover first because you do not feel comfortable with
I just have a question in general.
Yeah.
So is the final like from chapter 0 or whatever to 18, or did we go like past that?
We will cover stuff in separation. So we'll go through all of the stuff that we would have covered from 0, 3, 5, and then the acid-base stuff, the electrochem stuff, the spectroscopy stuff, and then into the stuff from separations. I'm still recording I'm going to record a video for you. So it'll be no more than an hour long. That'll cover some of the stuff like what do you do with a chromatogram and how do you calculate resolution and things like that. So you've got one more video to watch, but yes, we will get into some of the stuff from the GC and the LC chapter. Did that answer the question?
Yes.
Cool. All right. Very good question. Right. So in terms of like the separation stuff, which is a little fuzzy at the end, I want you to focus mainly on that slide stack that I have given you rather than the one that is the ones for the individual chapters, if that makes sense. Right, so there are individual chapters, and I've kind of combined some of them and smooshed them down into one set of slides for you. Okay, and we'll get to that at the end too. Like, what do you need to know about that? So, all right. So unless anybody else has another question. All right, so let's look at chapter 3 stuff. So chapter 3 stuff I just have pulled up here. So this is our experimental error. I'm expecting you to know basic things like kilo means 1,000. So if I'm talking about a kilogram, that's 1,000 grams. And milli means 1,000, so 0.001, milliliters. So you can do those types of order of magnitude conversion, and you can do basic stoichiometry stuff from Gen Chem. So I'm assuming that's kind of going along with just knowing general chemistry stuff. So for the treatment of error, right, that's this guy. All right, so you guys should all know how to do significant figures. Right? For us, it's really coming into play when we do our standard deviations. And our standard deviations have how many significant figures? 1, maybe 2, and then you truncate your answer to match the number of decimal places on your standard deviation or your confidence interval. How to do math with the sig figs. I think everybody knows that. This is why we've got sig figs. So let me do. I'll put a little star next to this dude, right? So that's important, 1 or 2. So that's your sig figs, right? If you know nothing else out of sig figs, I'm going to draw BAT, because that's what you're going to be able. That's what you need to be able to do, right? Is be able to do one or 2 sig figs, round it. All right. You should definitely know these. Right? Are different types of error: systematic error, bias, random error, noise, gross error. Know these and know how to deal with them. and be able to give me an example. All right. This would be a good example. A good example of what a concept question would look like. So something in the middle section of the exam. List 3 types of error. Give an example, and how would you deal with it? So that would be something that would be in that concept section of the test in that second section. So this would be a good question for that. And this is how do you deal with each of those? Right. So basically, systematic error you correct for by doing a calibration. That's your bias. You've got a couple of different sources, like know where they come from. Calibration, that's your key there. Right? And this is what that bias looks like on a spread of numbers. That's why we're using reference materials, random error. Random error, this is why we do statistics. So that's where our standard deviation is going to come in. Right, and then gross error. You should all know the difference between precision and accuracy. I'll put a little star next to it, right? That would be like a multiple choice level question, right? Is this precise? Is it accurate? Is it not precise? Is it both? Right, so this would be like a multiple choice level hard concept, right? So this would be multiple choice, but a conceptual multiple choice level. All right, and everybody's seen that. Okay. So yep, this guy, so error in a sum, right? So this would be something you would want to know how to do. Okay, I'm seeing a chat. No, we're going to go through stuff in separations as well. Okay. So know how to propagate your error in both multiplication. Right, so this guy, know how to use this equation. And then, where's the other one? And for this guy, know how to do this guy. Right? This would be something that would be in your problem solving. Right? So know how to do this in the problem solving. This would be a problem solving type of question. Here are 2 equations. What is the ultimate error when you get done with it? All right. So what were your 3 things that you had out of that? It was, what do you do with your standard deviation? How many sig figs do you put on something? Can you propagate an error? And what are your sources of error and how do you deal with them? So that's really 3 things out of chapter 3 that are the most important to me. Did you guys have questions about any of those things? And those ones are pretty straightforward. It's here's an equation. Where would people get tripped up would be in that problem solving if it's got both a multiplication and a addition subtraction step. So if you got like a combining multiplication and combining addition or subtraction, in that case, just follow your order of operations. Get the standard deviation or the error for the multiplication division parts first, and then throw it into the addition or subtraction. So it might take 2 steps and you might have to do both. Right. Questions on this guy? All right, I'm going to stop. I'll see if I can figure out how to get to this one. Okay, we're on this.
Is the final going to be coming from like the student written ones, or like are you having questions?
I will pick at least 1 student written question for each category. So there will be at least 1 student written multiple choice, at least 1 student written concept, short answer, fill in the blank, and at least 1 student problem solving. Make sense? Yeah, cool. All right, now let's do screen share, and we want chapter 4. All right, so chapter 4, looking at these guys. Come back, pen. Right, so know how to do this guy, right? An F test, know how to do a T test, know how to do a G test. This guy, you need to know how the linear least squares gives you data. Like if I give you something that's two different, I'm not going to ask you to compute one. No compute. Right? You're not going to need to know how to compute a linear least squares, but you are going to need to know how it works and what the information gives you, what the information type it gives you. Right? You should know the difference here. Right? Compare and contrast between our sample world and our ideal world, and when to use which set of statistics, whether you're going to use our ideal infinite world or whether you're going to use our sample trial world. Right? So am I going to use S for the standard deviation, or am I going to use sigma? Am I going to use mu for an average, or am I going to use X bar for an average? Right? And the important thing here is this n-1 for computing the standard deviation on your small real world trial. All right, so I'm gonna put a little star next to this guy because you will probably need to know how to compute a standard deviation. Okay, so yes, we can report stuff as TS over square root of n. We got variance and relative standard deviation. You don't need to know how to do those. I'm not gonna ask you to compute a variance or a relative standard deviation. All right. You should know the concept here, right? That the area under the curve, right? What a normal curve is, right? So that the area is equal to 1, right? And if we go out so many standard deviations, that you encompass more of the area under the curve for each standard deviation. I will not ask you to compute one. This would be a good concept question. All right, so what do each of these things look like? Oh, here's an outlier. Draw what an outlier would look like. What would a bias look like? You know, what does a detection limit bias look like? So if I messed with a Gaussian distribution, could you tell me what was happening to it? So could you tell me which one was more precise, right? So that's the one with the narrower distribution. So I'm not going to ask you to throw in particular numbers for this for your Gaussian distribution, but we'll see what else we can do. We got Q, standard deviation of the mean. Probably won't ask you about that. Pooling data only in the sense that, you know, right? Doing something like this would be a good problem-solving question. Right? And so this, right? Know how to do that. I'll give you this table if such a question shows up, right? But your job is to know how to use that table. Confidence interval. Yeah, you're definitely going to want to know how to do this, right? And the corresponding version for students T, where you've got X bar is plus or minus T times S over the square root of n. So you're using Z's and sigmas if you've got all the data, or you can measure enough of the population that sigma is really small, right? Or you use your sample standards and you're going to go with T's if you're looking at a small number of samples representing a bigger population. Okay. All right, so I would give you this if you needed it. Give you that. Put a star onto this guy. This would probably show up in your problem solving. That's the same thing with more numbers with it. All right, so t-test, yes. Be able to do a t-test. And so you should know in which case to use. All right. Are you looking at X compared to a known value, right? So I've got some reference standard. Am I comparing the same thing on two different instruments? Am I comparing yes, the Zoom meeting is going to be on Canvas. It will probably be a link to a YouTube just because I'm out of space on Canvas to store the actual thing. So the equations for the stat sheet will be on there. Yep. The stat sheet is posted in an announcement, so you can go ahead and look at that. What I did not have on that stat sheet is the periodic table, and I will give you a periodic table and the tables that you may need, like a T table or a G table or table of potentials for electrochem. So I just didn't want to give you like a table and then be like, oh yeah, here's a table. It's taking up all this extra printer space. As far as that equation sheet goes, if you want to print that guy out ahead of time, you may print that guy out ahead of time. Do not add to it. Do not put other things on it. Also remember that you do have a 3x5 card. You can print out the periodic table too. Yep. As far as the other tables go, do not print this out. And just because I want to make sure that you have the right version of those tables. If somebody gives you a messed up periodic table that you found, then that's just sad because that thing has not changed in years. So I feel safe with you guys printing out a periodic table, but like other ones, you might grab it might be listed as a T table, but it might be for a different application, or it might be a 2-tailed instead of a 1-tailed, and I want to make sure that you get the right table. Yeah, we can do that. All right, so now which T's to go with and when. All right, definitely know how to do this guy or a Q test. I don't care whether you use a Q test or G test, doesn't matter. Q test is very similar to G test. They're both doing the same thing. They're saying, oh, if I've got an outlier, what is it? So this would be, so these are real simple. This would be like a multiple choice level quantitative, because you're just going to throw in a couple of numbers, hit enter, compare it to a number. So there's no intense lift in the calculation there. It's a really simple, straightforward one. I'll put the little star next to this guy. All right, so you got to be able to do that. Will I be able to use my iPad for work and equation sheet? Yeah. I mean, you could do that. It's just going to be a lot easier to take a picture if it's me, but yeah, if you can figure out a way to make it work and like do all your problem solving and write out your work directly onto your device, that's fine too. As long as I can read it, that's the important thing. All right, G-test. Q-test is similar. I'm not going to ask you to compute least squares, but you do need to know that what it does is it gives you a line, and that line gives you a loop, and gives you an intercept, and it gives you some information, usually like R squared, about how close that line fits. I think that's pretty much it. Calibration curve or standard curve, yes. Right, if you've been in lab, you know that you have done a lot of these. You know how to do a standard curve, right? Here is a series of known standards. Here is their instrumental response. Here is my unknown. What do I calculate for its concentration X? To know how to do that. Yep, I would know what these guys mean, right? This would be probably like multiple choice or maybe a fill in the blank. Right? Define limit of quantitation, define limit of detection, right? Define limit of linearity. So what do you do if you get some, this is kind of an intriguing picture because it says, what do you do with your graph? Like here I plot up the data, what's happening to it. So if I can come up with a way to make an interesting concept or multiple choice question that says, if you graph your data, what is going on with it? I haven't done that before, so I will try to see if I can come up with a question that might be reasonable, but that's kind of a neat idea right here. It's like, here's a bunch of data. Because you graphed it, what did you learn after graphing it? I just don't know how to put that into words in an effective way. And these squares. Okay, cool. All right, questions about that chapter. So that was all about like our different tests, right? Our F, T, students T, GQ, LMNOP, XYZ, ABC, CNC, all of our different tests, right? Would we be able to use Excel if you had a graphing question, or should we print out graphing paper? You will get a question that will ask you to sketch a titration curve, right? If you want to print out graph paper for that, cool. You do not have to. I'm going to look at the table, and as long as you can freehand a decent looking graph for me, you can do that. So you don't have to print out graph paper, but you would not be able to use Excel. No Excel, graph paper, yes. All right. Next one.
Dr. Stewart, while you're looking for that slide, I just had a quick question, and you might have mentioned this on Friday or Thursday, but on the day of the exam, like, do we just get on Canvas at a given exam time? I guess, like, what's the structure?
Yeah, good, very excellent question. So what you're going to do is you will log in to Canvas at exam time. You will have a Zoom window up so that I can see everybody's smiling, wide awake faces. And so you'll have your Zoom on, your camera on, your mic open. You will pull up Canvas. I will have the quiz in Canvas. So the multiple choice will be as a quiz in Canvas, and I will set that for the entire time. And you can do them in any order. My suggestion is to do the non-multiple choice parts first. Right, kind of work the test backwards. So it's going to be in 3 sections: multiple choice, short answer, fill in the blank concept stuff, draw me A, X, Y, or Z, and then some problem solving numerical stuff, do that backwards, right? Because where are you going to spend most of your time? Is in that problem solving part. Can you make a random ass guess on that? Yeah, but it's probably going to be wrong. If it's multiple choice and it's A, B, C, or D, you can probably get that down to a 50-50 guess pretty quickly. So even if you did random guess on the multiple choice, you're still going to get more points than if you did random guess on the problem solving or the fill in the blank. Right? When you are doing things, right, do not leave things blank, right? Because I cannot give you any partial credit for anything that is blank. Right? The test is your chance to show me what you know, even if you start off by saying, like, I can't remember how to do this problem, but I know I need to do a student's t-test. I can't remember which equation it is, but this test will tell me that my two means are different, right? That tells me a lot, right? Even though you may not have gotten an answer for that question, it tells me that you know what the question is asking and basically how to go about getting it. All right, so write something, even if you're just like drawing a little picture of you looking confused, right? Maybe that'll be enough to kickstart your brain into going, oh yeah, I forgot this is this. And then once you start putting that stuff down, you may remember other things, right? So, you know, and worst case scenario, maybe you draw me a really hilarious picture and I'm like, hey, that's worth a point or half a point or something. So you will get partial credit for solution problems. That answers your question, yes. So the test is your chance to show me what you know, right? So, you know, it's not, oh, can I catch you out trying to do something? Sure, look out for things that might be stumbling blocks or trickily worded questions. I will try not to do that. Or if I do, sometimes I will say like, hint, be careful with, right? So that you know that there is maybe a little trickier stuff coming up. So yeah, you will log into Zoom, you will log into Canvas, which will have your quiz. You will have your 3x5 card, right, both sides. You will have your printout of your sheet if you wanted to print it out. So, you know, that's basically what we'll do is, you know, I will proctor you remotely over Zoom. Yay. Okay, I did find what I needed to do next. So that is coming up. Share and okay. All right, so those things are good to know, right? That would be a fill in the blank definition, short answer type of question. Define each of those types of samples. Right, know what matrices are and what matrix effects can do. Know your different types of standards. Yeah, this would be another fill in the blank, short answer level thing. But you should definitely know the difference between an internal versus an external standard. And if you are in the lab, you know, relate what you've got in lecture to stuff you've actually done in lab, right? Those two things are most definitely connected. So if we did something with an internal standard, right, or an external standard, right, relate those two things to each other. The more connections you can make, the better. So yep, these guys, right, I would know those and be able to define them. I mean, you should know that, but that's pretty straightforward. Right, more vocabulary terms here to know. Right, what are my different blanks? Definitely know what a matrix is. Oh, there's Spike. Little spikes on his tail. All right. Let's see, sample recovery. You should know how to do that. Method validation. Yeah, so know these. Right? So what are things that are important in an analytical technique? Right? So what's method sensitivity? What's accuracy? What's precision? What's range? Okay. All right, so know when to use this versus LOD is equal to 3 sigma or LOQ is equal to 10 sigma, right? If you have 2-dimensional data, use this. If you have 1-dimensional data, use these guys, right? You don't have to divide by M. It's this division by M, right? If you don't have a slope, right? You don't have a slope, you don't have to divide by M. So if you're like looking at what is the height of people in the room, right? There's no M value because you're just looking at a pool of one type of measurement, right? So here's where you're doing 3 sigma above the noise. There's no Y coordinate with it. It's just a bunch of X's. Standard addition. All right, so if you've got sample standard addition, this was our GCMS lab. You need to know when to do it. But really, that method of constant volume, that's what we're going to be looking for is if you have a plot like this, right, can you tell me how many or what the concentration is of your unknown? Okay. Do you need to use this equation? Yeah. But it's the same thing that you're getting out of this graph over here. And if you're me, right, now if I've got a y equals nx plus b, right, all I got to do is set y is equal to 0, calculate the absolute value of x. Yeah, constant volume. So that's just an example that goes through that. Internal standards are similar to that. It's just that here is we've got an internal standard each time. It might be varying a little bit. It's like this guy's like maybe 1.7, and this guy's like 1.8. Maybe this guy's like a 1.6. So if I see my internal standard varying a little bit, it lets me know that my instrument response is changing and fluctuating, and I need to multiply and renormalize to this guy, right? So, I'm going to divide it so that they're all 1.6, right? And then that means that this guy needs to be bumped down a little bit, right? And this guy that's 1.7 needs to be bumped down a little bit too, right? So, this guy needs to be double bumped down, right? And so that gives you a way to rescale your analyte to get a more accurate, it's an accuracy thing, result, right? And it's like throwing up a pickaxe to say, or a banana for scale, right? Here's my banana for scale, right? So you have a rough idea of how big something is, right? So is this Bigfoot cast really big? Well, here's a regular old foot for scale or a ruler. Yeah, you can do 1-point internal calibration. It's done, but it makes me uncomfortable. All right, and that's the end of that guy, all right? Questions about what you need to do for that chapter? All right, so if you had a linear least squares or a standard curve that was given to you, so it'd be something like I would do the data and I would plot it up and I would give you a graph. Could you figure out what the LOD was? Could you figure out what the concentration was of an unknown if it was a standard curve? Could you figure out the concentration of your unknown if it was a sample standard addition curve? So could you use those things, right? So it's really being able to use those. Okay. All right, so I want to look at the next one. Five. right, so now we're going to get into the actual chemistry stuff. So acid-base equilibria. This is assuming you already know, monoprotic. Assumes you, that's terrible, monoprotic and other equilibria. And so when we did this, we're like, okay, we got diprotic and acids and bases, and then it's pretty much the same thing as all of your polyprotics. But so acid-base definitions and concepts, right? This would be something that would be a short answer type of question. Can you define each of your different things? Hydronium. It's not on here, but I would say no. 5 strong acids and 5 strong bases. And 5 strong bases. So be able to identify a strong acid, be able to identify a weak acid, be able to identify a strong base, and be able to identify a weak base. That's what hydronium looks like. Activity, pH. Right, there we go. Memorize this. This is your generic expression for Kw, right? Remember that guy's temperature dependent. This is why we have our pH scale going up to 14. Right, so be able to interconvert between pH and H plus and POH and OH minus, right? So be able to go between any one of these guys. That should be just like a basic skill set, like, boom, I know how to go in between. If I'm given an H plus, can I find an OH, POH? If I'm given a pH, can I find an OH minus ion concentration? So if you got any one of these 4 square, any one of these guys on your 4 square grid, be able to go to any of the other guys. I will tell you, we are not going to do too much with like multiple iterative approaches. It's going to take too long. Right, so we got an expression for Ka and Kb, right? So yeah, you know this. That's what Ka looks like. That's what a Kb looks like. Right, so you should definitely be able to do this, right? Or use shortcut. If X is small. All right. If the percent dissociation is very small, you can simplify it. All right, so this is our simplified one. And this is only going to work if X is small. So when is X small? That's when you are 3 orders of magnitude separate. If you are taking a test, right, things you want to watch out for, a little danger sign, right? If K is, something times 10 to the minus 2, right? If you see this times 10 to the minus 2, you should be thinking, oh, danger, right? The other time would be if your concentration is going to be times 10 to the minus 4, right? And this is a low concentration, 0.0001 molar, not a lot, right? So X may be big compared to that initial concentration, right? So if you see a big K, right, meaning times 10 to the minus 2, or you see a small concentration, if your F sub C is going to be times 10 to the minus 4 or less, then you go, oh, wait a minute, I might need to solve the quadratic. If so, quadratic. And I will honestly not make you do that. Like this, way too much stuff to ask a reasonable question. Being able to apply this, yeah, you should be able to do that. That's just the quadratic formula split up for you, and with all of the variables in place to solve the quadratic equation, if you cannot make the simplifying assumption that x is small. If you need to, there is another one, and then that breaks down to your shortcut. Shortcut if small. Key part here is that you're going to treat these guys as successive. So even though you might have some sort of bicarbonate, and that's going to produce a monohydrogen carbonate, which can then further dissociate. If you were starting off with a bicarbonate form, you are not going to form much of the carbonate. So you're going to start off here, and most of it's going to stay as the H2CO3. And some of it will dissociate into H+ and bicarbonate. While this guy can dissociate again, the amount to which it dissociates is so small that we're not even going to consider it. So you would have to start off in the bicarbonate form to get yourself an appreciable amount of carbonate. K1 is always a big one. K2 is the next biggest one. K3 is next. It is hard to pull a successive proton off. You should know what a Zwitter ion is. Define that. Okay, amino acids are just good examples of polyprotic acids. They've got one, they got 2 or 3. So I definitely know this guy. I don't know what that word means. Amphoteric means it can swing both ways. This is the equation that you use if you are starting off at your intermediate form. So this is my intermediate form. So let's say we got H2A, and this would be starting off with just HA minus. So I'm starting off with HA minus. What is my H+ concentration? That's it. This is for an intermediate between K1 and K2. If you need to go further, these become K2 and 3, or 3 and 4. The big message out of this is you've got a teeny tiny amount, so small. So small. Okay. Get a teeny tiny amount here of whatever your fully deprotonated form is, if you're starting off with your fully protonated form. You got some, it's not 0, but it's 8 orders of 10 million times less. If you start off with your fully deprotonated form, it's mostly in your fully deprotonated form, you have very, very little. If you're starting off in the middle, in your intermediate form, you got some of both, but it's still mostly staying in whatever form you left it in. So when you're talking about weak acids and weak bases, remember they are weak, right? They're not going to form a lot of H+ and whatever your conjugate base is, and they're not going to form a lot of OH minus whatever your conjugate acid is. Otherwise, they'd be strong acids and bases. Diprotic buffers, right? Yeah, definitely know how to do Henderson-Hasselbalch. We'll put another star on here. Okay. Tell me what the pH is at a given point for a particular buffer. Right? When we saw these pH problems, two tricks were sometimes you might just have to find a ratio and then come up with another equation that gets you out of the ratio. So with a total ionic strength of 0.5, right, which tells you that the sum of your acid and your base forms have to equal 0.5. So A plus HA is equal to 0.5. That gives you another equation to work with. What I did see a lot of was if you, and I think there was either a homework or a quiz question. It was a quiz question where you had some sort of diaprotic species, right? And they wanted you to make a buffer that was like here, right? So this was the target. And you started off with your fully deprotonated or your fully protonated form. And so it was asking, well, how much did you need to add in? Well, you needed to add in like enough to get you to my H2A, that's got my HA. So you needed to get enough to go to the HA part first and then do Henderson-Hasselbalch to get you to where you need to be at halfway, right? And this would be the A minus 1. So if you get something where you have to go up a little bit first or down a little bit, maybe you started off up here and you need to do that, you need to account for the fact that you are in effect titrating the other species first. All right, that's that equation again. Know how to go between KB and KA. All right, so if somebody gives you a KA, can you find the corresponding KB? That's just there you go. KW over KA. All right, and so your weakest KA is going to be your strongest KB. Which is the principal species? Not so much of that, but right, these guys. A little star next to this, and then be able to interpret. And so here I've got a monoprotic, right? What the important information is here is like when I'm halfway gone, when my fraction is 0.5, that pH is going to give me my pKa. So the intersections here where they're hitting 0.5, that's going to give you pKa values. Right? You should also be able to say and interpret this and say, well, at a given pH, like let's say 6, how much of the one form do I have, and then how much of the other form do I have? And to be able to read that. All right, so if you're doing another one, again, you're looking for these intersections, that's going to give you pKa1 and pKa2. Right, being able to interpret them, just go to a particular pH or read it out. Isoelectric and isoionic. Right, and that's going to be able to define those guys. All right, those are polyprotics. What if you just solve it without SC? Will Canvas still accept? What do you mean, what if you solve it without SC?
Like if it was acceptable to use the shortcut, but you just decided.
Oh, that's a shortcut. So you are not going to have a numerical response thing for any of those. If it was a question, so Canvas is only going to be used for the multiple choice part of the quiz. Everything else you're going to write out by hand and then scan it and upload it to me. So
okay, got it.
You would have to be in a multiple choice question that would be like, what's the pH of a weak monoprotic acid with a Ka of 3 × 10⁻⁴? And then it would be a multiple choice question. So I'm not going to do a short answer type of, because that's just way too much. Like trying to do that for the entire test would be way difficult because, you know, Canvas on the teacher end of things, like getting Canvas to design and work those quizzes correctly is a giant pain in the ass. And getting it to do that for a final where people are under a lot of pressure, and if something goes wrong, you know, I don't want it to be people freaking out like, oh my gosh, it's within this range. And it's because like on that one quiz, you know, fortunately somebody noticed it before a bunch of people had taken it, but I had put in an extra 0 on one of the answers. And so instead of having like 0.016, I had like 0.0016, and you know, I can't have that happening on the final. So the final is just going to be, the only thing Canvas is going to do for me is the multiple choice, and then it'll be an assignment where you upload parts 2 and 3. Yes, I'm still dropping a quiz. Yes, one quiz will be dropped. Same thing if you're in lab, you get one free no questions asked lab drop. All right, let me end that guy. Discard. And nope. All right, acid-base titrations. Okay. In here, right, you should know that this is not going to happen. Right? You're not going to see a weak acid, weak base titration. For a strong acid, strong base, yeah, you should know that this pH is at 7. That's just because you're going to go quickly. If you're going to do strong acid, weak base, right, so your acid is strong, your base is weak, it's going to be below 7. Right? Because what's left over is once you've completely neutralized your weak base, you're going to have a leftover weak acid. Conjugate acid of the weak base. It's going to be weakly acidic. And so here you're going to be at a higher than 7. 7 if you're doing a weak acid being titrated with a strong base, because it's just the conjugate base that's left over. Okay. You guys have all seen this, and you get the basic idea. Like, to be able to tell me what the titrant is, right? Define titrate, titrant. All right, so how can you use a titration for quantitative analysis, right? If I've got a volume and I know the concentration, what is my concentration of my titrant? What is the concentration of my titrate? How to use the visual indicator, that's an important one. Right, be able to define these guys, right? Know the difference between an endpoint and an equivalence point. Right. Know that, yeah, this is your definition for your equivalence, EQIV, right? So it's got this little equal sign in here, my equivalence. And it's really saying moles of the titrant and the moles of the titrate are stoichiometrically equal to each other. And then you can disguise moles in different ways, either milliliters and a concentration, so volume and a concentration, or you could do it as a mass and a molar mass. The key is that you've got moles equal to moles. Streamline calculation. Yeah, that's an important thing to know. Okay, the general shape is the same. Right, because we're going to ask you to quantitatively do one of these, or semi-quantitatively. So how are you going to do that? So, yeah, so can you pick an indicator? Other things that you could learn from this is what is your Ka, right? So if I go between here and here, this is my equivalence volume, right? This at my half equivalence volume. And pH is equal to pKa, 1/2 equivalence volume. Let's see, yeah. And then know that before them there is a buffer, right? So you got the different regions on your titration curve. I got this, right? Here's my weak acid. Okay, this in here is my buffer region where I've got a mixture of HA and A minus. Here at my equivalence point, I've got just A minus. And down here at the very beginning, it is just HA. Right, so we've got a bunch of buffer. All right, hit a titration break, and then over here we've got excess with ACE hydroxide, H minus. All right, and you can figure out the pH anywhere along here, do an Anderson-Hasselbalch, but why waste time? Do it at the 1/2. All right, so this is when you are at this point, at your equivalence point, where you just have your A minus floating around in solution. You're going to treat it as a weak base. First thing you got to do is get this guy into a KB. And then you need to figure out what your concentration is. So then they're going to take it through this ice table, but it's going to break down to where you've got the concentration of OH minus, and you can do ice table. It's going to be the square root of KB times the concentration of A minus. Yeah, you can use your yeah. If it's on your calculator, you can solve it with the solver on your calculator. I am totally cool with that. The advantage of writing it out is if you put it into your solver wrong and it maths bad for you, right? That's an invisible process. So if you, to make your life better, write out the equation you're going to use, right? So let's say I need to solve this quadratic. I'm going to say, here's the formula I need to use. I'm going to do like Ka is equal to X squared over the formal concentration minus X. And then I'm going to do the next step where I actually throw in all the numbers. Right? So I'm going to leave X and I'll write out what the Ka is. And I'll write out what the formal concentration is. And then I'll do like, solve with solver and then write out what the numerical answer is, so that I know that you know what numbers are going into that equation. Right, so I can give you credit for saying, okay, dude picked the right equation. Okay, not only did they pick the right equation, they put the right numbers in. It should give them this answer, but they're getting something different. Maybe they divided instead of multiplied, or they missed a parentheses. Then, that'd be like minus half a point versus like, oh, well, mystery answer out of nowhere. I don't know where this number is coming from. All I know is it's wrong, right? So yeah, by all means, use that. Don't beat yourself up with the algebra, because that shit takes forever, right? So yeah, definitely use that calculator, right? If you need to type in a linear least squares thing, or have it do an F test or T test on there, because it'll do that, go ahead and do that. That's cool, right? Get the new equivalence point, right? So on a titration curve, your key points are going to be here, half equivalence here, and then out here at If that was 10, I would do it all the way out to 20, twice the equivalence volume. Right? At your equivalence, halfway, and 0. Right? So get 1, 2, 3, 4 points. Equivalence point, half equivalence point, twice the equivalence point. Figure out how to calculate the pH of each one. All right, so you're going to need those 4 points. You are going to need to sketch the curve that is in there when you are sketching the curve. Right? Little bump up here, mostly flat, right? But a slight incline. This probably needs to be sharper, right? And then this is going to be a sharper curve up here. Sharper, but not 90 degrees, right? This guy's going to be a little gentler. Right? And notice that this is going to take place over about, 1 to 2 milliliters on there. Right? And this guy is going to be pretty darn flat. Flat, or maybe a slight incline. Yeah, so this guy's what, maybe 10 degrees, 10 to 15 degrees up, right? So you're not going to give me something where you've calculated 1, 2, 3, 4 points, and then do some nonsense like that, or have it go up and over. Yeah, it's just practice drawing that little S-shaped curve in there. Right? Just a little bump up here, mostly flat. Right? It's going to go on a steady incline. Right? Take a real steep curve. As you start to get close to this equivalence point, goes up sharp, flat, and then asymptotically approaches whatever the pH was of your titrant. You should be able to identify like the strong acid or strong base, like know what's happening. So as you change your Ka and as you change your concentration. All right, so this is going to be change Ka. This one's going to be change your concentration. Right? So notice that the equivalence point is in the same spot. Right? You're just getting a sharper titration break as you're changing your concentration. If you were changing your Ka, you're actually changing where that flat point happens, right? Because you get, in effect, different buffers, right? For each of those is a little buffer zone. If you got a diprotic system, like here, it's just going to give you 1, 2 bumps instead of just 1 bump. I'm not going to make you do that. If I did, I would give you something like this where it's already got a nice first or second derivative on there. I'm not going to make you compute a derivative. But you need to know, like, here's my derivative. That's going to tell me what my endpoint is. Right? So if I gave you this, the question I would ask would be, what's EQ1, right? What's EQ2? Right? That you could tell me. I'm not expecting you to be able to generate this on the fly. And real world data is often not nearly as nice as that. And I'm not going to ask you about a grand plot. If I gave you one of these, could you figure out what the end point or the equivalence point and what the halfway to equivalence point is? Yes, to be able to do that. I would try not to give you one where you'd have to actually print it out, because you're not going to be sitting there with a ruler on your screen drawing lines. I would give you a table of indicators. Your job would be to know which one to use. Be able to pick right. Pick the right one. And we all know why not to eat the phenolphthalein. You should know what a primary standard is, right? Be able to define that guy. I would have a big old list. If I'm doing this, I'm going to have a big old list of all of my vocabulary words for each chapter. I'm going to go through each chapter. I'm going to look for all the bold words. I'm going to write them down. I'm going to write down a definition that comes next to it, and then I'm going to write that definition out again in my own words. Okay. Questions about that part? Cool. All right, let's see what we got next. Calibration, acid-base titrations. All right, electrochem. Now we're getting into newer stuff that you may not have had as much exposure to. Okay. Pushing cat. He's so quiet. Okay, so looking at this, right? Basic concepts, galvanic cells, a standard potential, Nernst equation, and going between K and E, right? So E, so our E cell is going to be equal to our E naught minus 0.0592 over N log of Q. Right? So we've got really, this is going to be E left minus E right or whatever. Right, so standard potentials, those are the things we're looking up off the table. Nernst equation is what if we're under non-standard conditions. E naught and equilibrium constant is just saying I've got a relationship between E and K we can use. All right, so polishing a penny, we can do lots of cool things. Aluminum is awesome. Yeah, you can bounce a battery. All right, you've got two basic things. One is going to be our galvanic or voltaic cells. The others are electrolytic cell. Do you generate electricity or do you use electricity to generate a chemical reaction? Right. You should definitely know either Leo says GER or oil rig, or I've only got so much space in my brain, which is number goes down, it's reduced, right? All right. So if I'm looking at this guy, right, I'm going from a zinc solid into a zinc 2+. Right, this is easy to identify as an oxidation, right? If you find something that is a solid, right, kind of focus in on that because it's only going to go, it's not going to go more solid, right? It's not going to go to a zero, extra zero. Right, so your solid is either going to go to a minus or a plus. Right? It's usually going to go to a plus if it's a metal. That's going to be the oxidation. If I flip that around and my solid is my product, that's a reduction. Right? So a reduction is, in this case, hydrogen gaining electrons. Right, and you get some pretty colors out. You should be able to know what's happening up in molecular scale. So know molecular scale. I think everybody's pretty good with that. Okay, here's my copper, and here's my zinc, right? An electron is coming off of the zinc, and I'm forming zinc 2+, right? Which means that the zinc is getting oxidized on my copper 2+, is picking up the electrons, it's getting reduced to copper solid. right? And that's a pretty cool little demo, right? Where it's actually depositing, in this case, silver on top of the copper, right? Here you've got zinc, copper is depositing on the zinc. Here you've got silver depositing on the copper, and the copper is getting oxidized. And that's because of their relative positions and the relative electrochemical reduction potentials. Right, so be able to do assigning oxidation numbers, right? Definitely be able to do that. I don't think anybody had any problem with these types of questions. Knowing how to balance something and balance a redox equation, right? So you should be able to do that. It is a long, complicated process, but you're still going to do it the half reaction method, right? If you got to do it, and if I ask a question where it's like balance this, it's going to be doing it this way rather than doing something with electron following, which is the old way to do it. The old way to do it, if you've got something simple like our copper silver reaction, where it's really easy to see, I don't have any complicating oxygen species, it's just the two metals. I can figure out how many electrons are going on with that. Otherwise, you're going to have to do this longer method of balancing things. But it's got a series of steps, right? Write out the half reaction, right? And then you're going to do non-OH. So no hope at the beginning, right? Then once you've got that, then you go for the O by balancing out by adding water. Then you're like, oh crap, I added a bunch of water. And then you balance it out by adding H pluses. Once you do that, you then balance top to bottom. So these are all left to rights on your equation. Like, so I got some unbalanced by adding some hydrogens. Now I got to add, or adding some hydrogens in my water. Now I got to add some hydrogens by adding some acid. Then next you're comparing top to bottom, the reduction and the oxidation to make sure the number of electrons match. So here you've got 6 electrons over here. Oh, sorry, you got to match the charges. So I got to add some charges, add some electrons over here to balance this out. So I've got +6 and +6 and +2 and +2. Then you're going to balance out and make sure that those electrons match up for both the oxidation and the reduction. Right? And so then you add them both up together. Right? Balancing it at a base, same basic stuff, but then you're adding in an OH on the side to counteract the H pluses. Right? Same setup. This is where it starts to get different. You got 14 H pluses, and then you're making it in base, so you're adding hydroxides to both sides. Right. These guys cancel out to form water. You got 14 waters over here, 7 waters over here. You simplify, just leaving you the 7 H2Os. We talked about Faraday and how he's kind of a badass, and Alessandro Giuseppe, Antonio, and Stasio Volta, which is just fun to say. We talked about Frankenstein, and we want to set these guys up into half cells. Calculating the total charge, right? You should be able to do that guy. I will give you Faraday's constant. Electrical work. Relating it to Gibbs free energy. All right, this guy is important. If calculated delta G would be a good question, like calculated delta G for an equation given a cell voltage of 0.23 volts. We should know that our galvanic cell has 2 halves. All right, we've got be able to draw and label. Right, and this would be something in your short answer. Right, so draw and label an electrochemical cell with, you know, zinc and copper, right, and show what's happening to each electrode. So be able to draw this, label the anode, label the cathode, show me which way the current is going, show me which way the electrons are going, what is my reduction reaction, what is my oxidation reaction, right? So calculate the voltage if these things are working under standard conditions, right? So there's a drawing question here, right? Give me this figure, both labels. Know what your anode is and know what your cathode is. Be able to do one of these, and be able to do a line notation. All right, I got about 4 minutes left. I can keep going. Do you guys want me to keep going? I don't know if people got to cut out. Okay, I'm going to keep going and go overtime. If you need to leave, this will be posted online. Okay, so that we can go through this. I just want to make sure that I go through all of the stuff we got to go through. Okay. Yeah, be able to do that. Let's see. Yep, this guy be able to go from G to E, and vice versa. If I give you an E, tell me what G is. If I give you a G, figure out what E is. All right. Our EGK love triangle, where we're relating K and E to each other via delta G, right? So minus RT ln K, or minus RT over NF ln K is going to be our E cell. Right? Know that when you are at equilibrium, E cell is 0. Right? So this little table is important to know. And this is important to know. This was from Gen Chem, so we don't need to know that, but we do definitely need to know this guy. Our molecular view, inactive electrodes. This is just showing what happens if you got an inactive electrode instead. All right, this is a good question. All right, so calculate your 3 values. What we did not talk about was our delta S and our delta H. That's coming from our delta G. So, you know, that's coming from Gen Chem stuff, so I would not ask you necessarily how to calculate this, but like this type of question, I'm like, yeah, that's kind of cool. It's a little table. Like, here is an E cell, maybe calculate G and K for that. What's K? Right, we're just using this relationship here, right? So K is going to be related to delta G over RT, which means that we can get another equation where we're going to relate G to E cell. Nothing happens. Got our salt bridge in there. Right, there you go. It even says know this, right? Which ones are attracted to the cathode? Cations are attracted to the cathode, which means that anions are attracted to the anode. And the anode is going to be on the left, and the cathode is going to be on the right. Right? That's alphabetical order. How to do your sign notation? Yep. I'm not going to be able to do that. Our standard potentials, we said, are all going to be relative to our saturated or standard hydrogen reference electrode. And so our E cell, that's just our delta G is equal to minus NFE. All right, so this, that's important because that's how you're going to calculate your stuff from the table. Right, so this is their table value and another table value. Right, so you might see this instead of right and left, you might see this guy as cathode and anode. Right, you could also write it as the sum of a reduction and an oxidation potential. Right, however you choose to do that, as long as you're getting correct answers, that's cool. So yeah, this is, we're going to have a table of half cell reactions. Right, so we can pick and mix. 1 reduction and 1 oxidation. All right, so yeah, you should be able to definitely be able to do an E0 calculation. Right. And this would be like multiple choice level quantitative guy. Can you subtract 2 numbers on a table? Are you subtracting the correct ones? Are you subtracting them in the correct order? SHREs is terrible. All right. So I would give you something like this. If you needed it, or if I'm feeling generous, I will actually pick out which things are the ones you need, but I will always give them to you as the reductions. I will not give you them as oxidations. If you need to make it an oxidation, you flip the chemical equation, and then you change your of each type from each category. No, I do not know. That's not an off question at all. So I do not know what the distribution is going to be. I'm not going to be like, we've got 10 chapters. I'm going to pick 1 multiple choice question from each chapter. No, it's going to be like maybe 20 multiple choice questions, and I will try to distribute that evenly across the chapters. Some chapters are not going to have the same distribution, though, in that multiple choice. Same thing with, especially in the problem solving. So, you know, you may get some more problem solving out of one chapter versus another, right? So, you know, you might see like 2 on the chapters 0 through 5 because those really lend themselves to computation, like calculate a standard deviation, right? That's a calculation problem solving thing. Whereas the stuff with, you know, some of the spectroscopy stuff is not necessarily going to be as computationally intensive. So I will try to balance the overall thing so that the points, the total points are going to roughly be representative of each chapter, but you may get some uneven distribution of those. But I will try to make it as flat as I can. Right, so some of the electrochem stuff, you know, like lends itself to draw a electrochemical cell, for example, right? You know, so that would be a short answer question. You know, there's a little bit more conceptually type stuff in there than there is in the, you know, sensing electrodes, right? So, you know, so how that's going to distribute, I don't know exactly, but I will try to keep it as even as possible, but you may not get 1 multiple choice from each chapter. So I will try to make it as fair and doable as I can to cover as evenly the material that we've got to cover. So I'll give you the table. You should definitely know how to do that. You should definitely know that the magnitude and the sign are important. You should know that it is not spontaneous, right? Because our potential is negative. You should be able to identify, this would be like a good multiple choice, right? Multiple choice, or maybe an FIB, right? Of these 2, which is a better oxidizer? Fluorine or magnesium, right? And you're going to go, well, fluorine's an awesome oxidizer. Yep, these would lend themselves well to like multiple choice type of questions. This would be, if I were to convert that, I would probably convert that to a problem solving question and then make you make math happen and make the math happen. Okay, definitely know how to do a Nernst equation. All right, when you're looking up the Nernst equation, you can think of it as being like the Henderson-Hasselbalch, right, where we had, you know, pH is equal to pKa. We got some sort of starting position, and then we're going to adjust it in some sort of loggy way. Right. So here we're starting off with what is our standard state cell potential, and then we're going to adjust it based on the temperature and then where we are with our product versus our reactants. So most of the time we're going to take this 2.303 RT over F, kind of ball all these together at 25 degrees C. It's one constant. You know, be able to do these, right? So this is a good example. And that guy's a good example. Figure out my cell voltage if I change my concentration of one of these. If you see something like this, where have I seen people get caught up, is like, if the reaction is 90% complete, you know, make sure you get the right numbers in here, right? So when I do 90% complete for this reaction, my amount of Ag plus is going down. My amount of copper 2 plus is going to go up. But keep in mind that this guy is going down twice as fast as this guy's going up. So don't forget basic stoichiometry has to happen too, right? So 90% complete would be, I have used up 90% of my Ag. How much more Cu did I make? Right? So this guy's going up and this guy's going down. Okay. One of the things you can do is you can Nernst equation both halves of the equation separately. So you could do a Nernst equation on the copper and figure out what its actual cell potential is at that condition, and then do a Nernst equation for the Ag. Have a 1 over the Ag concentration squared, right? Don't forget your squared up here because this guy's got a 2. So what its concentration is, and then treat them as the sum of two potentials. That's a good one. It's important to know. Yep, you should be able to do this. Right? If I give you a K, can you find the E? If I give you an E, can you find the K? K to E. And the other one we saw before was E to delta G. Diagram stuff. Not in K, it's the same thing. How do you measure pH? All right, so I would want you to know what a formal potential is and why you have it, but not necessarily compute anything with a formal potential. And that's the end of that. We got batteries. How does the battery work? So if you've got your regular fundamentals down, all it would be, you know, does this equation make sense? And you should all be able to do that. You know, I don't think I'm going to ask you to draw a battery, like draw and label the components of a battery. You know, if I give you a battery question, it would be something where I would give you I would give you the overall equation and then ask you another question, and the battery just shows up as flavor text. Electrolysis, yeah, you need to know what it is. Let's see, I think that's it. Okay. Basic electrochem questions. acids. Now, do that. Sulfuric acids, covered those. Covered that. Okay. This one. Okay. Analytical techniques. All right. So our electroanalytical techniques. Right, they're coming into really a couple of categories, right? Excuse me. Coulometry, right? This is your sensing electrodes, and like your pH probe. Right? Coulometry, that's where you're measuring basically like a charge, and then amperometry, that's where you're measuring a current, and voltammetry is also measuring a current, but this is like your CD stuff. And then we did not do the Carl Fisher. So, electrogravimetry and coulometry. You should know what a working electrode is and a counter electrode. Fine. Why are you using them? What are they doing? All right, your working electrode, that's where the fun stuff happens, and then your counter electrode is just a place for the electrons to go. Right, this Q equals IT. This is a nice short quantitative guy. This is a good question. How many grams of copper were deposited? Sorry about the sound. Right, IR drop, right, you should know what that is. And over potential, right? And over potential, I'd be able to define those. Right, I would know this equation. Know what this guy means. Using a 3 electrode cell, you should be able to draw one of those and explain, right, what are each of the things doing. Polarization, right, you should be able to define that. And we got 2 sources of polarization, both kinetic and concentration. Right, that'd be a no or a draw. Okay, I should be able to draw this guy. And these you should be able to know and explain what each one is going to, how each EACH can cause polarization. All right, so this is our full version where we got some sort of potential. It's going to be related to our cathode and our anode. We need to put in a little bit of extra for our IR drop, and then a little bit for our over potentials, which is coming from here. So I'd be able to draw that guy. All right, measure the over potentials. I probably would not. I would know the idea that surface area and effects are important, right? Because that's where all of your interesting stuff happens, is at an interface. You know, I wouldn't ask you to reproduce this, but I might say, like, why are the surfaces more important, or why would the steps be more active? Excuse me, electrogravimetry, we would cover that in the Q is equal to IT part. Coulometry, that's our Q equals IT. This is the thing where it's like, okay, if I leave a 9-volt battery hooked up to a solution of copper, how much copper would plate out on my electrode after 3 hours? These guys. That'd be something worth knowing. Is how are they controlling for potential interference? Okay. So let's see, our voltammetry. You know, be able to ID a technique. What's each one good for? What are the pro and cons of each technique? You know, which pulse profile with what method? So, you know, I would know that the limiting current is going to be related to our concentration times some fudge factor, K. I would know about E1/2 and what's the importance of E1/2. Right, so if I increase the concentration on this guy, right, my limiting current is going to happen in the same place. Right, so this is concentration 2 and at concentration 3, right, my limiting current just goes up and up and up. This is my half wave voltammogram. Right, my half wave potential. You should know that you've got 3 regions, 3 regions. So you should get to draw and label that. What's happening in each part. I will give you this. I'll give you this equation, right? But the important things to get out of here are really this I, right? So my I is going to be related to my concentration, and usually that's how you're going to see things. It's going to be as your concentration, and that K, when we go back to this guy, where our limiting current is K times A. One of those rare chances to actually see a K broken out for you, where it's N times the Faraday's constant times the surface area times the diffusion times the change in concentration. So that's where that K is coming from, but usually it's just a BK. Right? So if I gave you a thing where we had like, here's a bunch of these, you know, could you do a conversion into a standard curve, that current and concentration? And then from an unknown, figure out what was the unknown's concentration. Rotating disc electrode, I'm just going to tell you we're not going to ask about that. Yeah, could you do this? if I give you a series of voltammograms, could you convert that into here? And then let's say you've got something that comes in here, what's its concentration? Okay. And you pick the right electrode. Right, and that would be a multiple choice type of question. So if I'm working in a solution of 1 molar hydrochloric acid and I'm trying to analyze iron with a reduction potential of minus 0.2 volts, what electrode would I work? What would be an acceptable electrode? You know, A, B, C, or D. You know, I might even, I would even give you this on there if I needed to ask that type of question. All right, so definitely know your stuff from cyclic voltammetry. All right, what is going on here? What is going on here? All right, so in other words, can you label the parts on here, like what's happening at this point? All right. Know if it's reversible or not reversible. Right, so this guy is reversible. This guy is not reversible. So they're not one. Okay, so to be able to do this guy, so you should be able to tell me the number of electrons. And so if you've got a cyclic voltammogram that looks like this, ooh, that's terrible. All right, I can figure out my delta E, and then from that I can figure out my number of electrons. All right, Randall-Sevick equation, I would give you that. But that is going to be relating the area, the concentration, diffusion, sweep rate, number of electrons to this peak current. So how high up will this go? Again, that's related to the concentration. So yeah, you could do another standard curve, right, where I'm plotting IPC as opposed to insane clown posse, which is ISP or XCP. Yeah, you should be able to tell if it's reversible or not. You should know that that guy's going to depend on the sweep rate. The faster you go, the faster is going to give you more peak. Right, so if I real fast, my peak actually goes up. Like if you see like something like this, you should know that each of these represents a separate reduction or oxidation. Polarography, really just what do you get out of this? What is your E1/2? What is your average current? And again, you're looking at information that E tells you, what is it? And then the I is going to give you your quantitative information. So this E is going to be kind of qualitative. Right? And this I is going to be your quantitative. Right? And the important thing for this is that you've got the mercury drop electrode. And then you've got different pulse profiles. You could do a regular pulse, or you could do a differential pulse, and it kind of syncs up your drops with the pulse rate and gives you a slightly different derivative looking. Right, so from here, I would expect you to know if you saw one of these, you'd be able to find this E1/2 value. Right, this peak would be E1/2, and then this peak would be your E1/2. And that. Screen, electrodes and potentiometry. What's important with this? Knowing what your reference electrodes are, knowing how your indicator works, what's a potential and how do your ion selective electrodes work. And those are the important things out of this guy. So you've got a potential that you're making, right? You're always making a potential measurement. You're going to make one of these guys a reference, right? And you're not going to use a standard hydrogen reference electrode most of the time. It's going to be something else. What makes it a good electrode? What makes it a good E-reference, right? And then you're going to measure this potential of whatever your test solution is relative to that reference electrode, because your voltages are potentials. They're always going to need 2 points. What is your reference is really important. So it's a half cell fixed composition. These things that have a solid and a saturated solution, the concentration of your saturated solution is pretty stable at a given temperature. That's why we're going to see things with the calomel and with the AgCl electrode, where it's going to be something in a saturated solution so that the concentration does not change. So we've got a couple of different types, right? The simplest being, here is our reference electrode over here, and then we're going to make some sort of test solution where we've got something in solution and then a sensing electrode. Our reference electrodes, right? We got a couple of different ones, the AgCl and your saturated calomel electrode. One is using insoluble mercury, one is using insoluble silver. Right? There are pros to using each kind. Most of the things we're going to see these days are going to be silver, just because it's safer environmentally. Each of them is going to have a particular voltage or offset relative to the SHE, which means that when you make your measurement, you got to adjust it by whatever that reference is. So be able to do this guy. Right? What is my measured voltage for a given reaction with this as my reference electrode rather than an SHE? And all it's doing is it's offsetting your SHE standard potential. Sensing electrodes, we said there were a couple of tricks you can do. Right? Your basic one is where you got the metal and then you're putting it in its own solution. This is the equation you would want to use for that. So be able to use this guy. And so there'll be something like, I've got a silver wire stuck into a solution of silver ions and I get this voltage. What's my concentration? So you're going for this guy usually. Right? You could actually rearrange this. I might have it on that sheet where, because this is like, here's a negative and here's a log, right? You're going to find an equation for P, whatever the metal ion concentration is. All those dang P functions. Right? So these are working where you get the value from the table. You've got a concentration, and this guy's in PAG. Yeah, so I think I would have given you this as well. If it's not on there, let me know and you need it. Figure out my concentration. Concentration unknown solution. You can flip that and do it the other way and measure your anion if it's insoluble, and really you're just measuring the Ag plus concentration and you're replacing K in there for whatever your anion is. Right? So you're switching it around. You're not really measuring the Cl minus directly, you're measuring it indirectly by measuring the Ag plus concentration. So you should know that this guy, right, know that the slope is going to give you that, and that your indicator is going to give, or that your intercept is going to give you your E naught value. So what can you learn out of these? Junction potential. Right. Define junction potential and illustrate. I'd definitely be able to do that. Yeah, but how do these things work? Yeah, they're all going to work in the same way. So be able to draw and explain your membrane. So how do these things work? They're all doing the same trick. You got some sort of porous membrane. You got a reservoir on the other side. You're looking at, well, what is the difference in concentration on the outside versus on the inside? Yeah, I don't think I would ask you to draw that. But, so you know how this works. All right, so what's happening here? We've got a reference, and then what's on the outside? You know, how is that pH meter working? And so I would not give you this, and this guy I would give you. All right, so you would need to be able to generate that on your own. This I would give you. That part with the hydrated gel layer, yeah, I know that. You should know what the alkaline error is. I don't think I will ask you about the selectivity coefficient. Not that it's not important, but I don't think we got time to ask about it. I got way bigger things to ask about. Yeah, but that's really just the same as the pH one. All right. And we saw some of these, so I'll be able to draw this guy maybe. Draw and explain. That's it. I'll be using the ion selective electrodes. No, nothing about that. Building field effect. Okay, that's the end of those. Share screen. Okay, so for this one, it's spectroscopy. Let me blow through this guy. Right, you should know your terms. I know those guys. You should certainly know that light is a particle or wave. You should know and be able to do this. I will give you this. Yes, definitely be able to do this guy. All right. This is a nice table. I like that guy. You should be able to do that. All right, so you can know the relationship between these two things. You can know why those are happening. I'm not going to ask you specifically about those. Let's do that. Yeah, I know that what your counter colors are. Definitely know Beer's law. This guy has a good question. Right. Deviations to Beer's law. We know that the absorbances are additive, which means you can do things in a mixture. You know, to explain. Black body radiation. Okay, so you should be able to draw those. Right, know what each of these parts are. Know your parts. Sources. This is good. You do this. Draw and explain. You definitely know this. What the grading looks like. Explain, not math. Be able to draw at least one. Be able to draw and compare. Interferometer was the thing with that, and I would know that it's, you know, if needed. Yeah, you should know the different types of noise, and you should definitely know that signal averaging is important. Okay, and then fluorescence. Explain what's happening here. Able to draw one of these guys. Okay. And one more, and that's our separations. Separations, you should know the basic concepts. You should know that we are going to mainly do column chromatography. You should know this partitioning coefficient concept. You should know what a mobile phase and stationary phase is. You should be able to tell, you know, what's reversed and what these guys are. You should be able to know what all these are. Know that. This is important to know. 2 ways to increase separation. You definitely want to know this guy and this guy, right? So be able to calculate K, be able to calculate an alpha. You should to know how to calculate the number of theoretical plates in a column. The fact that these guys are going to relate to each other by length and plate height. You should be able to know this version of the Van Deemter, right, and where each term comes from, right? Be able to know and explain each of those. Let's see. This right here, this is quantitative. Quantitative, and it's going to show up. It's going to show up in that problem solving. Right. So knowing how to do this, right? Both calculate and R. Let's put a double star on this guy, and how many theoretical plates I would need to affect a particular resolution. Right? That is a really good quantitative question. Gas chromatography, you know, maybe sketch this, and then you don't need to know so much about the sample injection system. This, like what's going to happen with this and the temperature, that's important. Knew that. You don't necessarily have to know, but I would be able to draw. We'll draw at least one. We didn't talk about this ionization over different times. So mass spec, this is what we did in lab. Knowing about this temperature profile, that's important. For the LC, yeah, I know the difference between gradient and isocratic elution. I think this is how CE works. And then this picture is important for that. Your flow profile. And this is how. So these guys for the capillary electrophoresis. All right. That is all of the things. So I'm going to end this. And I know if somebody wanted to see me after to go over a test, I will meet you there pretty shortly. You can't see rums. I'm not sure what. Okay. What could you not see? Was it the separation stuff? Okay. So it's really being able to do the stuff with the R. Yeah. That was. Meeting, share screen. Two. And that's all of these guys. So I want to go through these real quick. You should be able to see it, right? It's knowing that how the separations are working. So like this stuff over here, where we've got the stationary phase versus the mobile phase. What's going on with partitioning? Which things are going to come out the column first? What are the variables that we need to do? Particularly focusing on resolution. To do that, you're going to need your retention time. How are you going to focus up these two things and get a good separation? How do you calculate K? So it's this retention time, and what is your total? What's your total retention time? So TR minus TM. That's just how long the first peak comes out. Calculating this guy for alpha. Knowing how many theoretical plates are coming off of your column based on the peak width. And that's going to change for each thing that you go through. Being able to calculate the number of theoretical plates or plate height. Here's an equation for plate height. Knowing what each of these terms are. checking to see, okay, is this guy a liquid or is it a gas? The stuff with resolution here, this is what the quantitative question would be, is what's coming in with, here I've got two peaks, A and B, what is the resolution? What would I need to get to give me a given resolution? That's being able to work these two equations, super duper important. And then, you know, knowing what temperature profile will do for a GC and what a ideal detector is, but also with the isocratic elution versus the versus a gradient elution would do. So in gradient elution, you're changing the composition of your mobile phase to make it get these peaks that are slow to come out faster. So it's basically doing the same thing the temperature does for GC. But that's about it. Oh, the flow profile. So like, how does the capillary electrophoresis work? But I think that's it. All right, I'm gonna meet with somebody or two after this. So give me like 5-10 minutes to save it and upload, and I'll meet somebody back here about 5-10 minutes.